Welcome everybody to the PALS seminar today. Our speaker today is Will Bryan, and he's going to talk about partitioning the real line into Borel sets. Please.
All right, well, thank you. So yes, I'm going to talk about partitioning the real line into Borel sets. I'm going to start with a fairly simple observation, which is that if you'd like to partition the real line into some finite number of Borel sets, then you can do it. It's not too hard to figure out how to do it. You probably didn't need a picture of it for me to show you a picture to understand how to do it, but there's a picture anyway. I've been told it's always good to put a picture on the first slide. So here's another one. You can partition the real line into Aleph zero Borel sets. I guess one interesting fact that I can mention is that you cannot partition it into Aleph zero closed sets. So sort of the obvious way of partitioning into intervals, they should all be half open and half closed, or maybe half of them open and half of them closed. But you can't partition it into any number greater than one of open sets, or any countable number of closed sets. But anyway, these half open intervals are fairly simple, certainly Borel, and easy to get any countable number of them. So the question is, what about partitions into uncountably many Borel sets? And I'm going to start just by defining the answer to my own question to be this object. So I'm going to denote by SP Borel the set of all uncountable cardinals kappa, such that there is a partition of the real line into kappa Borel sets. I'm restricting to uncountable cardinals simply because the situation for countable cardinals is not very interesting. Yes, you can do it for all countable cardinals. Okay, fine. And so now the question becomes, what can we say about this set of cardinals? The Borel partition spectrum is what I'm going to call it. What can we say about it? Well, 3 facts. First of all, Aleph 1 is in the Borel partition spectrum. So I had been attributing this fact to Hausdorff, because you can prove this using the existence of what are called Hausdorff gaps. But when I gave a talk about this work a few months ago, and Cy Friedman was there, and he actually informed me that there's work of Luzin and Sierpinski predating Hausdorff's work by about 15 years that actually implies this already. So to get a partition of the real line into Aleph 1 Borel sets, you can first split it into an analytic and a co-analytic set. And each of those is the union of Aleph 1 Borel sets. And so you get a partition into Aleph 1 Borel sets that way. All right. Hausdorff's work is still relevant in that it does allow you to put a nice bound on how complex the Borel sets are. You can make them all F sigma delta sets, so fairly low in the hierarchy. And it turns out that Hausdorff's F sigma delta is optimal there. So it was proved decades later by Fremlin and Schella that you actually cannot do it. It's consistent that you cannot partition the real line into Aleph 1 G delta sigma sets. So F sigma delta is the best you can do in ZFC. All right. What else? Well, the continuum is in the Borel partition spectrum, and it's the maximum thing in the Borel partition spectrum. This is pretty obvious because you can partition the real line into singletons, and those are all Borel, and there are continuum many of them. The one other interesting thing I have to say about that is simply that it's kind of a funny thing. Without the axiom of choice, it is actually possible to partition the real line into more than the cardinality of the real line, many Borel sets. Pretty strange, but anyway. I'm going to be assuming the axiom of choice for the entire rest of the talk. I just wanted to mention that because it's a really cool fact. Okay, third fact about the Borel partition spectrum. It's closed under singular limits. So more precisely, what that means is that if we have a singular cardinal lambda, and the Borel partition spectrum contains unboundedly many cardinals below lambda, then it must also contain lambda. And I'm going to sketch a proof of that because there's a fairly nice and simple argument for that. So here's a sketch of the proof for the special case that lambda has cofinality omega. So what you can do is, okay, if we're unbounded below lambda, that means we can find a sequence of cardinals, kappa n, such that lambda is the supremum of these cardinals, and each of these cardinals is in the Borel partition spectrum. So then we look at the real line, and we carve out countably many intervals, maybe the intervals from n to n plus 1, And each of those intervals is homeomorphic to the real line. So that interval can be partitioned into kappa n Borel sets, each of them can. So we just partition each of those intervals, the nth one, into kappa n Borel sets. And then we get a partition of the real line by tossing in, putting all those separate partitions together and then tossing in the one extra set, the set of all leftover points that were in none of those intervals. That's a closed set, so also Borel, and of course it doesn't increase the cardinality. So there you go, you have a partition into lambda sets. And that's it. So this is the complete list of known ZFC provable theorems concerning what we can say is in or is not in the Borel partition spectrum. Or really, I guess just what is in. None of these theorems say something is not in there. Well, maybe the second one does. Things bigger than C are not in there. Okay. So fine, this is all that's known, and okay. Can we prove that there's nothing left to prove? This is the next question we want to ask. So we have this list of theorems. I've sketched one of them for you. One of them is obvious, and the first one, well, I wasn't planning on getting into that. So what I want to talk about is whether there's anything left to be proved. And this is, the way to answer this sort of question is with forcing, with independence results, with trying to find models of set theory that show there are no other limits by essentially making the Borel partition spectrum look like anything you want it to look like, subject to these three constraints. Can we do that? Well, okay, there are a few independence results about the Borel partition spectrum. So in historical order, it's consistent with any permissible value of the continuum that the spectrum is everything from Aleph 1 up to C. What do I mean by any permissible value of the continuum? What I mean is that if there's a forcing extension that makes the continuum equal to Aleph alpha, then there's also a forcing construction that makes the continuum Aleph alpha, and also makes this other statement true, that the partition spectrum is everything from Aleph 1 up to that Aleph alpha. So assuming that the Aleph 1 of the constructible universe is the true Aleph 1, then Harrington found a way to do this way back in the 70s. Much later, Arnie Miller and I found a different way of doing it. We weren't really trying to improve on Harrington's result. We were actually ignorant of Harrington's result. And we just tried to think of some way of proving this. And what we came up with doesn't use any assumptions like that. So starting from any ground model, whatever you can force the continuum to be, you can force it to be that along with making this true as well. Okay, it's also consistent with any permissible value of the continuum that this Borel partition spectrum can be as small as possible. So remember, it has to contain Aleph 1, it has to contain the continuum. It's consistent that that's all it contains, no matter what the continuum is. Okay, this is a theorem of Arnie Miller from a very long time ago. What else? Well, this last one here is essentially, it extends both of these results 4 and 5. I just wanted to list the others for historical context, but this last result is really trying to say that we can make the partition spectrum look however we want it to look. And so the idea is that we have a set of cardinals, and our set of cardinals is going to have to satisfy 4 different requirements, which I'll tell you what they are in a minute. But the idea behind this theorem is that if we have a set of cardinals satisfying those 4 requirements, and if we furthermore assume that GCH holds, some fragment of GCH holds in the ground model, then there is a CCC forcing extension which makes this set of cardinals into the Borel partition spectrum. So I know that maybe not everyone knows a whole ton about forcing, but let me just say very briefly, a CCC forcing extension, what's important about that is that CCC extensions preserve a lot of sort of natural facts about the ground model. So if you start in some model of set theory, and then you do a CCC forcing extension, then the ordinal that used to represent, say, omega 2, the second uncountable cardinal, still represents that uncountable cardinal. You haven't added a bijection from omega to that ordinal that now turns it into some very big countable ordinal or anything like that. So a lot of things about the ground model are preserved. It's sort of a nice tame extension, but using these nice tame forcing extensions, we can still make any cardinal equal to the Borel partition spectrum subject to these 4 requirements. Here they are. Requirement number 1. We should assume Aleph 1 is in our set of cardinals. Okay, we know that we had to assume that because we know Aleph 1 must end up in the Borel partition spectrum anyway. So requirement A, fine, it's unavoidable. Requirement B, also unavoidable. So it's disguised a little bit, but this is simply a way of voicing our requirement that the continuum is going to be in the Borel partition spectrum. So we know that the spectrum must have a maximum, namely the continuum. And if we're going to turn a cardinal into the continuum via forcing, then it must satisfy this cardinal arithmetic relationship. So this must be true if we're going to turn the max of C into the continuum anyway. So again, this requirement here isn't really anything that we shouldn't expect. It's a pretty innocuous requirement in that sense. C must require this, or this must be required of C if we're hoping to turn C in the Borel partition spectrum. Same for the third requirement, closed under singular limits, again, because we know the spectrum is. But there's a fourth requirement. So if we have a cardinal in C and its cofinality is countable, then the successor of that cardinal must also be in C. Okay. So let me just go ahead and say, let me just go ahead and say that a few months ago, this list of requirements looked a little bit different. There was a fifth requirement in my original proof of this theorem. I needed a fifth requirement on C, namely that C be countable. So this is a recent improvement that we can get rid of that requirement. The improved version is not just my theorem anymore, it's joint with Vera Fisher. But anyway, that's yet to be written up. But anyway, this is any list of any set of cardinals satisfying these 4 requirements can be turned into the Borel partition spectrum. So the only suspect requirement is this fourth one here. All right. So in other words, what I just said, right? The Borel partition spectrum can be nearly anything that does not directly contradict our ZFC provable theorems about it. So for example, we can always force given any set of integers, as long as 1 is in there, there's a forcing extension in which that set of integers represents all of the Aleph n's that are in the Borel partition spectrum. So for example, it's consistent that there's a partition of the real line into Aleph n Borel sets if and only if n is a power of 17. Okay. However, as I already mentioned, item D on our list does not correspond to any of our ZFC provable theorems about the spectrum. And so what I want to do in the remainder of the talk is sketch a proof that even though it's, item D doesn't correspond to anything on that list, it corresponds to something that almost made the list. So there's a theorem that I'm going to state for you and then sketch a proof of for you. That essentially says we can't get rid of requirement D without, at the very least, invoking large cardinal axioms. All right. So that's where we're going. So here's the theorem. The main theorem, whose proof I want to sketch in this talk, is that if we assume that 0 dagger does not exist, then if kappa is a singular cardinal with cofinality omega, and it's in the Borel partition spectrum, then its successor must be as well. Okay, so in other words, going back to this previous slide here, it says exactly what requirement D is saying here. So under this assumption that 0 dagger does not exist, whatever that means, we'll get to that in a minute. Under this assumption, these 4 requirements here on our set C are now exactly the things that we're able to prove about the Borel partition spectrum. And therefore, these are exactly the things that are provable about it, because this theorem here says that anything else goes, and there's nothing more you can say about the structure of this set of partition sizes. Okay. A corollary to this is that if you ask about anybody's favorite singular cardinal, well, of course, it's Aleph omega. So if we look at the first singular cardinal, Aleph omega, if there's a partition of the real line into Aleph omega Borel sets, but not Aleph omega plus 1, not its successor cardinal, then that means that 0 dagger does exist. And so what I want to say about that, I suppose, is that 0 dagger is this, saying that 0 dagger exists is a large cardinal axiom. So zero dagger is not what you would strictly call a large cardinal, in the sense that it's not a cardinal at all. But what it is it's a little bit like zero sharp. Zero sharp is maybe more familiar. Zero dagger is a set of true statements about a certain well-structured set theoretic universe, not Gödel's constructible universe L, that's zero sharp, but extensions of L that involve large cardinals, that involve measurable cardinals, in fact. Anyway, saying zero dagger exists is a little bit like saying not only are measurable cardinals consistent, but actually measurable cardinals are consistent in a very strong sort of way. We have models of containing measurable cardinals that are very sort of small fragments of the set theoretic universe, small and well understood fragments of the set theoretic universe. But at any rate, all we really need to know for the purposes of this talk is that if zero dagger exists, then there are inner models containing measurable cardinals. All right. So the goal is to sketch a few of the ideas that go into proving this theorem. And there are two main ingredients to the proof. So two main things that I'd like to talk about before we get to the proof sketch. And those things are cofinal Kurupa families in this poset here, which I'll define in just a moment. And also a lemma that I'm going to prove for you, a lemma about partitioning large, completely metrizable spaces into Polish spaces. So here we go. The poset square bracket kappa to the omega, what is it? So square bracket kappa to the omega is just notation for the set of all countable subsets of kappa, or countably infinite subsets of kappa. But when I talk about it, I'm usually not referring just to the collection of countably infinite subsets of kappa. I really want to think of it as a poset. So the poset is ordered by inclusion. So an extension of a set is just any strictly larger set, any set that includes it. Well, not necessarily strictly larger set that includes it. And probably everybody here knows what cofinal means. So when you have a poset, a cofinal subset of the poset means that everything in the poset has something in your cofinal set that extends it. So here that is, with specifically extension meaning containment or inclusion. And then what is Kurupa? So Kurupa is maybe less familiar. Kurupa in this context means that for everything in the poset, for every countably infinite subset of kappa, if we take our family F and restrict it to that one countably infinite set, then we only get countably many things. So there may be, and in fact there will be, assuming kappa is uncountable, there will be uncountably many B's in our family that meet A. But the point is that even though there are many sets that have to have non-empty intersection with A, many of those sets will have the same non-empty intersection with A. And if you look at all of those intersections as a collection, you only get countably many different things. So hopefully it'll become more clear if I give some examples. So for example, if I look at the entire poset, it's a subset of itself, it is cofinal, obviously, but it's also not Kurupa. The reason it's not Kurupa is simply if I look at the poset restricted to A, I get all subsets of A, right? All subsets of A, and that's an uncountable set. So I get uncountably many ways that other things in kappa to the omega can intersect a given thing in kappa to the omega. On the other hand, a countable subset of kappa to the omega is going to be Kurupa, but not cofinal. One way to think about this is that cofinal subsets are big and Kurupa families are small. So if a family is cofinal, then any strictly larger family remains cofinal. If a family is Kurupa, then any strictly smaller family remains Kurupa. But the interesting ones are when it's both. So if we have something that's both cofinal and Kurupa, that can be very useful. So one example of that, my only really easy example of that, is if we look at kappa, just omega 1, the first uncountable ordinal, and we look at the set of all countable but infinite ordinals. So first of all, I'm using the standard von Neumann notation here, where an ordinal is considered to be equal to the set of all its predecessors. So when we think of an ordinal that way, each countable ordinal alpha is a countable subset of omega 1. So this is, in fact, a subset of this collection here, the collection of countable subsets of omega-1. It's cofinal. Why? Because if I have any countable subset of omega-1, it's also bounded and therefore contained in one of these alphas. So it's cofinal, but it's also Kurupa because, again, if I have a countable subset of omega-1, it's bounded, meaning everything up to some alpha may meet my set in different ways. But after some fixed ordinal alpha, I'm just going to be containing the whole thing anyway. And so after alpha, all of my new ordinals, all my betas greater than alpha, are going to intersect my countable set in exactly the same way. In fact, they're just going to contain all of it. So most of the things in this family F just intersect a given countable set in the entire countable set. And the restriction of F to A is, in fact, countable. Okay. A theorem of Todorcevich. If we have a cardinal less than Aleph Omega, less than that first singular cardinal, then there is a cofinal Kurupa family in this poset here. This is just a fact, provable in ZFC. But not easily. It's actually surprisingly difficult to prove, I think. If we have a cardinal beyond Aleph Omega, at or beyond Aleph Omega, then we can still ask whether this is a cofinal Kurupa family in this poset here, but it's no longer provable from ZFC. There is going to be one, however, provided that square lambda holds for every singular cardinal lambda. So what does that mean? Square lambda is a set theoretic principle, which I'm not going to define. Actually, the definition is a little bit complicated. And if you're not already familiar with it, it's frankly a bit hard to follow. But the important point for today about square lambda is that this set theoretic principle also follows from an anti-large cardinal axiom. So in fact, if zero dagger does not exist, then square lambda holds for every singular cardinal lambda. Actually, square lambda failing for some singular cardinal gives you even more than the existence of zero dagger, but at least it gives you zero dagger. So by the contrapositive, the negation of zero dagger tells you that this holds. Okay, so another fact about cofinal Kurupa families is that if one exists, then it must have the minimum possible size. So what do I mean by the minimum possible size? The minimum possible size of any cofinal family. If the family is also Kurupa, it must have precisely that size, can't be bigger. Despite the fact that any bigger family is still cofinal, any family that's bigger in cardinality will stop being Kurupa. Okay. And now we get to this theorem of Dodd and Jensen, or at least I don't know if they ever stated explicitly, but it follows from all of their inner model theory work that they've done. So assuming zero dagger does not exist, all right, then what happens? Well, then square lambda holds for every singular lambda. So this is all that I mentioned earlier, right? That square lambda holding for singular lambda, it follows from this non-existence of zero dagger. Okay. Furthermore, we also have a pretty straightforward way of knowing what the cofinality of this poset is. We just look at the cardinal kappa, and if kappa has uncountable cofinality, then the cofinality of that poset is just kappa. If kappa has countable cofinality, then the cofinality of that poset is kappa plus. But either way, we know exactly what it is. And in particular, and this is really how I'm going to use this theorem. So in particular, what it says is that if we have a singular cardinal with cofinality omega, then combining what Todorcevich's theorem says with what this theorem of Dodd and Jensen says and what that sentence in between says, what we get is simply we get a cofinal Kurupa family in kappa omega, where the cardinality of this family is exactly kappa plus. Okay, so moving forward, this is really all we're going to use about the non-existence of zero dagger. So all we really need to know about zero dagger does not exist is this sentence right here. We're not going to use any other facts about it. So this is really all we need to know. It means there exist these cofinal Kurupa families, and the size of such a family is going to be exactly kappa plus, assuming kappa is a singular cardinal with cofinality omega. Okay. So here is the thing that I think on a previous slide I called a lemma. So here is the lemma or theorem, as I labeled it here, about large, completely metrizable spaces. So assume zero dagger does not exist. if we have a singular cardinal with cofinality omega, and we let D denote the discrete space of size kappa, then there is a partition of D to the omega into kappa plus Polish spaces. So one thing to note, if D is a discrete space, so I give it the discrete topology, that is a metric space. The distance between 2 points is 1 if they're different or 0 if they're the same. So that's actually a complete metric space. And so when I raise it to a countable power, I still get a complete metric space. So this is a completely metrizable, I should say. This is a completely metrizable space that looks a lot like the bare space in a lot of ways. So the bare space is omega to the omega, countable discrete space to a countable power. This is kind of like that. We're just starting with a much, much bigger discrete space. So think of it as the bare space, but much wider. Okay, and I claim we have these nice partitions of it in the Polish spaces. So, okay, what do we do? Well, using the assumption that zero data does not exist, as I said, all we're going to use that for is to get this cofinal Kurupa family of size kappa plus. So we're going to look at the post set, not kappa to the omega, but square bracket D to the omega. So this has the meaning just all the countably infinite subsets of D. Okay. The existence of cofinal Kurupa families depends really just on the cardinality of this thing here. So earlier it was a cardinal, now it's a set D, but that doesn't really change much. So we have a cofinal Kurupa family of size kappa plus. What do we do with it? Well, first we well order it. We fix an arbitrary well ordering of this family. And then for every set in the family, we're going to define X sub A to be exactly this. So we look at A to the omega power. So A is a subset of D. So A to the omega is a subspace of D to the omega. So we look at A to the omega, and then we take away from it the union of all B to the omegas, such that B is also in our cofinal Kurupa family, but it precedes A in our well ordering. Okay, fine. So what I'm going to argue is that this is actually, this is the partition of D to the omega into kappa plus Polish spaces. So there are a few things to check. First of all, what are we looking at here? So, what kinds of things are these X sub A's? Well, I want to point out that if A is in this family F, then just by definition, that means A must be countably infinite. So the space A to the omega as a topological space, A to the omega is really just a copy of the bare space, omega to the omega. So up to homeomorphism, that's all it is. The bare space up to homeomorphism, by the way, that's just the irrational numbers. So up to homeomorphism, A to the omega is a copy of the irrational numbers. It's also a closed subspace of D to the omega, closed simply because A is closed in D. So if A is closed in D, which is true because D has the discrete topology, that makes A to the omega closed in D to the omega. So we have this closed set here, and I'm removing a bunch of other closed sets, namely all these B to the omegas. Okay. So first, I'm going to argue that, oops, I'm sorry. Oh, no. I was about to apologize for a typo, but now that I look at it, I don't think it is a typo. These A to the omegas are a cover for D. They're not my partition, but they're a cover for D, meaning that every point of D to the omega gets into one of these sets, A to the omega, as A ranges over F. So why is that? Well, okay, to see that that's true, let's pick a point in D to the omega. And a point in D to the omega just means that we have a function from omega to D. So if I have a function from omega to D, I look at the range of that function. That gives me a countable set. It gives me countably many points of D. And because F was cofinal in square bracket D to the omega, that means that something in my family must contain that countable set. But if A contains that countable set, X at every point, then that means that X itself is in A to the omega. So that's it. That means that these A to the omegas form a cover of D to the omega. Why is that important? Well, it follows that the X sub A's form a partition of D to the omega. So remember how the X sub A's are defined. Let me go back to this previous slide here. So what I'm doing here is I'm taking A to the omega and removing all of the previous B to the omegas, right? All the B's and F that came before A in my well ordering. So if we look at, so we know that some given point X is in some A to the omega. So if we just look at the first with respect to my well ordering, the first A to the omega that it gets inside of, then it doesn't get removed, and it's actually in X sub A. So there you have it. The X sub A's are also a covering because of how we define them and because the A to the omegas are. But if they're recovering, they're also a partition because each X sub A, I've explicitly removed everything that went into all of the previous X sub B's. So, okay, we have a partition of d to the omega. Fine. If we have a partition, that's really not everything. The partition seems to have the right size because F has cardinality kappa plus. I'm waving my hands here a little bit. But instead of focusing on the size of F and proving that it really is kappa plus, I just want to point out why the X sub A's are actually Polish. So why are the members of this partition actually Polish spaces? Well, in order to see this, you need to recall a fact from topology or from descriptive set theory, however you want to look at it. But if you have a subspace of the Baire space, it's going to be Polish if and only if it's a G delta subspace. Those mean the same thing for subspaces as the Baire space. So G delta, okay, countable intersection of open sets. Well, here is our definition of X sub A. It's A to the omega, remove all of the B to the omegas, where B ranges over F and the B came before A. Okay, but that's the same as A to the omega, remove all of these sets. And instead of all of B to the omega, it's okay just to remove B intersect A to the omega. Essentially because any points in B that aren't in A, we don't care about points of B to the omega that include those things because those aren't in A to the omega to begin with. We really only need to remove the points of B to the omega that are in here. Okay, but now what are we doing? Well, we're essentially looking at the restriction of B to A. We're looking at the restriction of B to A as B ranges over F and precedes A. So because F is Kuropa, this thing here, the set of all B intersect A's, such that B is in our family and precedes A, it's just some subcollection of the restriction of F to A, which was a countable set, because that's what Kuropa means. So we're really only removing countably many things of this form. And when we remove countably many things of this form, well, it's a closed set minus countably many closed sets. That's a G delta. So we have a G delta subset of A to the omega, which makes it a Polish space. All right. So that's a sketch of the main lemma. And now I'm going to sketch a proof of the main theorem. So this theorem, again, let me remind you, it says that if zero dagger does not exist, then if we have a singular cardinal kappa with countable cofinality, and if it's in the Borel partition spectrum, then so is its successor. All right. Oh, by the way, sorry to interrupt myself here. I just want to make sure you guys can still hear me, right?
Yes.
Yes.
Okay,
Yes.
good.
Yeah.
Sorry, all of your pictures were to the right-hand side of my screen, and then all of a sudden they all disappeared. So I was hoping my computer wasn't misbehaving and had logged me out. Just wanted to double check so I didn't give the rest of my talk to, my coffee cup. Okay. So anyway, here's the theorem. I've reminded you what it says. Let's look at the proof. Suppose kappa is a singular cardinal with cofinality omega, and suppose there's a partition of R into kappa Borel sets. So we want to try to prove that there's also a partition into kappa plus Borel sets. Okay. We can go ahead and just subtract all the rational numbers from everything, and basically it doesn't affect much, right? So if we start with the partition of the reals into kappa Borel sets, we can remove the rationals from the reals, and we can remove any rational numbers from any of our partition pieces. We still end up with kappa partition pieces. They're still all going to be Borel, but now they're subsets of the irrational numbers, which, as I mentioned earlier, the irrational numbers are homeomorphic to the Baire space. So essentially what we get is a partition of Baire space into kappa Borel sets. Turns out that's going to be easier to work with for this proof. So let's start there. Instead of the reals, let's say the Baire space. Okay. If P is such a partition of the Baire space into kappa Borel sets, that is, then the next move we want to do is we want to just multiply everything by the Baire space. So I take everything in my partition and I multiply it by the Baire space, and what do I get? I get a partition of the Baire space times the Baire space into Borel sets. But it turns out the Baire space times the Baire space is just homeomorphic to the Baire space. It doesn't actually change the topology. So we get a partition of Baire space into kappa Borel sets, each of which has the additional property of being nowhere sigma compact. Now this is important because going back to Luzin and Suslin again, although I actually come to think of it, I may have spelled their names differently on the other slide. But anyway, going back to Luzin and Suslin again, if you have a nowhere sigma compact Borel set, it's actually the image of the Baire space under a continuous bijection. So this is a very useful fact. So each of these kappa different partition pieces we can think of as the continuous image of the Baire space under a continuous bijection. So just sort of plopping all of those different continuous bijections together, we can consider it to be one giant function from kappa many copies of the Baire space. So that's what this is here, right? So D cross the Baire space. D is the discrete space of cardinality kappa. So we have one giant continuous bijection from kappa many copies of the Baire space onto the Baire space. It's still continuous because each of these component maps that we're slapping together was continuous. And it's a bijection because each of those components was a bijection and their images formed a partition of the Baire space. So we get a continuous bijection from D cross omega to the omega to omega to the omega. Okay. And now we raise everything to a countable power. So when I say everything, I mean, we look at this map we had earlier. We take the map itself, take the space on the left, we take the space on the right, and everything gets raised to a countable power. So in other words, what I'm talking about here is the diagonal map. So it's denoted like this, f to the omega of what? Well, the domain of this diagonal map is just the power of the original domain, the countable power. So D cross Baire space to the omega. So this means functions from omega into the space here. So I'm just denoting that function as a countable sequence here. So what does f to the omega do to this countable sequence of things from the original domain? It just applies f to each of them individually. And so what we get with f to the omega is a sequence of things in the original codomain, hence the original codomain to the omega. And it turns out, it's actually not too hard to check, that if the original function is a bijection, then f to the omega is also a bijection. And if the original function is continuous, then f to the omega is also continuous. So what this means is that we have a continuous bijection now from the power D cross Baire to the countable power onto Baire to a countable power. And now we're just going to observe that taking countable powers didn't do anything to the right-hand side. So the Baire space to the countable power is still the Baire space, but it did do something interesting to the left-hand side. So whereas before we just had kappa many disjoint copies of the Baire space just sitting next to each other, when we raise that to a countable power, we actually get D to the omega. So instead of a bunch of copies of the Baire space next to each other, we now get this sort of much wider version of the Baire space. This space, if you recall, that was the topic of our previous theorem or previous lemma. So, as you might guess, this is the point where we apply that previous theorem. So let me remind you what it said, right? It said, assuming zero dagger does not exist, then we can partition that space D to the omega into kappa plus Polish spaces. So that's what we're going to do. Oh, I guess I don't actually say that's what we're doing. But back to this slide here. So we have a continuous bijection, big F. We have a continuous bijection from D to the omega to omega to the omega. So now what we're going to do is we're going to partition the domain of that function here, this D to the omega. We're going to partition that into kappa plus many Polish spaces. And we can do that because of the previous theorem, because we're assuming zero dagger does not exist, and that's what it tells us we can do. So, okay, let's take P to be such a partition. We partition D to the omega into kappa plus Polish spaces. And then what do? Well, we have this continuous bijection from the previous slide. And, oh man, that's a typo, my mistake. This should be a capital F here. So we define this new partition Q, excuse me, to just be the image of P. So we take every set in P and we push it forward from the domain of this function capital F to the codomain. And so what does that do? Well, when we push forward a partition of the domain, we get a partition of the codomain. So we get a partition of Baire space. The partition has the same size, so it's a partition of size kappa plus. And all of these sets are what? Well, again, Luzin and Suslin come to the rescue here. There's a theorem that says that if you take the image of a Polish space under a continuous bijection, you get a Borel set. If you don't say the word bijection, by the way, then you don't necessarily get a Borel set, right? This is a very famous mistake of, oh goodness, I'm blanking out, may have been Borel himself. So if you have a continuous image of a Borel set or of a Polish space, it might not be Borel, it's just analytic in general. But when you take a continuous bijective image of a Polish space, you always get a Borel set. So each member in our new partition is in fact Borel. And since the bare space, as we mentioned a few times already, is homeomorphic to the space of irrationals, we have a partition of the irrational numbers into kappa plus Borel sets. We can toss one extra set in there, the set of rationals, and we get a partition of the reals into kappa plus Borel sets, and that's what we wanted to prove. So that's it. That's the proof of the theorem. All right. I want to point out that this theorem can be extended in a few ways. So the word Borel there, we can replace it with compact, closed, F sigma, analytic, anything on this list you see here, and the theorem remains true. For everything analytic and beyond, actually no. For everything in this range, this is essentially because sets like that can be partitioned into Aleph 1 Borel sets anyway. For these things, you can just redo the proof and look at what the proof gives you when you start with these sorts of things instead. And for these things, you need kind of a different idea, but it's a similar idea. These are all just sort of extensions of the same sort of thing. We also get, this is interesting to me because I'm really more of a topologist than a set theorist, to be honest. So for me, this is kind of where my interest in this sort of thing started a while ago now. But if we take a discrete space of size smaller than Aleph omega, then we can ask the question, is there a continuous bijection of d to the omega onto, say, the unit interval? And the answer turns out to be related to this whole Borel partition spectrum. So there's a continuous bijection from d to the omega onto the closed unit interval, or really onto any Polish space, it turns out, if if and only if there's a partition of the reals into precisely that many Borel sets. And if we look at sets bigger than size Aleph omega, I'm sorry, that should actually be bigger than or equal to. We can include Aleph omega there as well for this. Oh, actually, no, that's another non-typo that I tried to correct because I'm assuming the cofinality is bigger than omega anyway. So we can ignore Aleph omega for this part. But anyway, if we assume zero dagger does not exist, then the same applies to larger discrete spaces, provided the cofinality of the cardinality is uncountable. Unfortunately, I don't really know if this is true when you look at spaces, discrete space of size Aleph omega, for example. All right. That's pretty much all I wanted to talk about. I'm looking at the clock here, and I think we're supposed to end. Oh, no, I made this mistake earlier. I thought my talk started at 3:15. That's 3:15 my time. And I logged into our meeting 10 minutes early. Now I'm trying to log myself out 10 minutes early as well. Okay, I think I can tell you what my questions are, and then we'll still have a good 10 minutes if you have any questions as well. So anyway, the questions that I wrote down, these are, to me, the natural questions raised by this line of research. These are the things that I still don't know how to do. My main open question is this one right here. My wife informed me she would be very angry if I tried to offer cash prizes the way that Erdos used to, but if I were to offer a cash prize for solution to any question that I know, it would probably be this one. I would love to know how to do this. I currently have no idea how to do it. Let me point out that if it is consistent relative to some large cardinal hypothesis that this sort of thing can happen, then we'll know. Then we'll know exactly what can and what can't be proved about the Borel partition spectrum. But at the moment, it's possible that my theorem I've proved from zero dagger does not exist. It's possible that that is actually provable from ZFC. You just need different ideas to do it. So until this question is answered, I can't really know whether there's that one last ZFC theorem still to be proved about the Borel partition spectrum. Okay, next question. You remember one of my corollaries was, well, the theorem stays true if Borel is replaced by a whole big list of other things. I would really like to add G delta to that list. G delta is important for a number of reasons in this context, but in some sense, it's an interesting question just because it seems to be very hard and it seems not to follow from any of the techniques that I have so far for looking at this sort of thing. Another thing that I don't know how to do, what's the minimum size of a partition of the reals into uncountably many G delta sets? For all I know, it could be the case that this is equal to a known cardinal characteristic of the continuum. So the covering number for the meager ideal. So this just means the number of meager sets that it takes to cover the real line. So it's an uncountable number, provably less than or equal to the continuum, but consistently equal to just about anything you like. Let me point out that if this is Aleph 1, then it's very easy to show that there is a partition of the reals into Aleph 1 G deltas. But if this is bigger than Aleph 1, it all of a sudden seems very difficult to say anything at all. And that's a question I'd be very interested in knowing the answer to as well. And finally, here's a more formalized version of what I said on the previous slide, which is that I really don't know about these continuous bijections from D to the omega. I really have no idea what happens when D is a discrete space of singular size. And so that's all this last question is saying. It's still true that if you have a partition of the real line into Aleph omega Borel sets, then you do get a continuous bijection from D to the omega onto the interval like this. But whether the converse is also true, whether there being such a bijection implies there being such a partition, that I don't know anymore. But anyway, that's it. That's all I have.
Thank you very much for your interesting talk.
You're very welcome.